Okay, hello. My name is Marvel Imanuel Susant, and today I will present the tensile test result that had been held in Sampoerna University mechanical engineering lab. So, firstly, there is something that is important before doing the test, which is the stress and the strain, because the stress and the strain will determine the uh, displacement, and also um, we can find the uh, Young modulus from from the ratio between the stress and the strain. So stress is the force per unit area, while strain is the deformation per initial length. And there's also the gauge line that will there is the certain area that we will measure the displacement, and the specimen using the dog bone is regarding to the standard for metal. So the apparatus, we will use the 313 universal testing machine with capacity maximum in 50 kilonewtons. So firstly, this is a procedure. First, we will measure the dimensions of the specimen, and then we will clamp it in the testing machine, and then we run the test. And before that, we need to set up the device or the software in the laptop so it can record for the stress for each time step. Okay, so this is the result from the test from aluminum, and still this is for the metallic specimen. And we can see there is the area of the necking that I give a red circle there, and that's actually break into two. And both of them, um, the fracture is happen in the gauge area. And this is for the HDPE and the PLA. For the HDPE, we can see there is the necking is so long. We can see that there is no breaking, but the elongation, it can be more than the initial length. And therefore, and this is the PLA. I think the PLA, uh, I I don't have the result picture. So this is the result for the measurement before and after. The initial gauge length, the middle part, the measure one, all the same 50, but the one that we need to pay attention in the initial and the final, we can see there is the different, and each specimen with different material has different um, elongation. And then we can see for the biggest material that can receive the force is steel. So we can, from here, we can assume that steel has the highest strength. And then for next, after we gained and got all the value from the testing for each time, we can find the Young modulus, which is the slope of the linear line or the elastic region. We can find 2 points, and like we finding a usual slope. And then for the yield strength, it can be measured using, this is using the 0.2% offset, which is uh we added 0.002 to the strain line, and then we give a parallel line to the linear one, and then we can see the intersection point is the yield strength, and then the ultimate strength, we can see the highest is the for the steel, and we can see the longest elongation, it must be the HDPE, but I don't have the data yet. later on the report. I will give it. Okay, so that's for the data. And here's for the graph. The graph here shown for the still, we can see that the yellow one is the offset, and from the offset line, we can see there's the intersection, which is the red dot here. It shows around 280,000 kilopascal, and for the ultimate strength, it is 420 kilopascal in the highest point, and for the fracture strength here is 350 kilopascal at strain 0.36. And from here we can see that the behavior of the steel is firstly they have elastic region, and then starting to deform plastically, and then finally reaching the ultimate tensile strength, and finally ductile, and then finally fracture. So this is the comparison for the theoretically, or someone who has doing the research about this. Because there's some difference actually from the shape. It's kind of different, and then the yield strength and the steel. For the yield strength, they're also different value. Why this can be happen? Because first we can say the composition of the steel. There's a lot of kind of steels. Maybe it is an alloy or mixed with something, which can affect the strength and the ductility. This is the source. And then next, this is for aluminum. And using the offset, also we can get that the yield strength here is 180 kilopascal. And for the ultimate here, for the highest point is at 212, 123 kilopascal. And for the fracture, the end of this line is 171,720 hundred. And we can see the elongation is 6.16%. So the behavior of aluminum is ductile metal, no sharp yield point, and moderate elongation. Next, we can compare our result with the theory. We can see there's also a difference within the shape, and the reason is the same as before. Because it can be happen due to the alloying composition, or maybe in the manufacturing process, and the definition method used to define the yield strength. For example, like 0.2% offset for yield. And then this is for the PLA. I'm using 0.2% offset as well. And we can get that the yield strength here is 38.6 megapascal. There is the red dot here. And then the ultimate tensile strength here, the highest point is 41,340 kilopascal. And for the fracture, the end here, after it dropped to 28,878 kilopascal. And PLA here have a behavior is brittle polymer, and we can see the elongation is very small. And lastly, this is the HDPE. Using the same method, we can get that the yield stress is 14.3 megapascal, approaching the literature, which is 20 until 40 megapascal, and the UTS is the top one here, is 21,413 kilopascal, and for the fracture strength here, the N is 14,577 kilopascal. And I think this will be the longest elongation in this task. And also, it can be from literature, it can be 400 under 600%. And also this material is very ductile. But before fracture, it exhibits snacking and plastic deformation or permanent. And there's also the so-called slip phenomenon. So slip phenomenon is a plateau or a horizontal line appear with almost zero slope after elastic region, and this mostly appear in mud stills. Why this can be happen? First, there might be a dislocation motion while doing the tests, or maybe there is an impurity or interstitial atoms like carbon or nitrogen, and also it depends on the material type and the strain aging. What's the effect of this phenomenon? It can produce visible leaders, bands, and cause non-uniform deformation on onset of plasticity. And here, the question, why ceramic have bigger young modulus, but um, yeah, but it easily to fail. Yeah, because the behavior of ceramics is very brittle. It is stiff, steep slope in the stress strain curve, but very brittle. Compared to steel, which has lower modulus, but it is less stiff, but has high toughness, ductility, and yield strength, where it allowing plastic deformation and energy absorption before fracture. While ceramics, there is no elastic region, so it's easily fractured. Yeah. And in engineering net, structure requires not just stiffness but also the safety against sudden failure. So, before we have been mentioning, I've been mentioning about what is about toughness. So, what is basically toughness? By definition, toughness is the ability of a material to absorb energy before fracture. This can be represented by the area under the stress strain curve through the x-axis. And what is the behavior for this toughness for each type of material? For example, for ceramics, it's very stiff, and still because it's very stiff, it has a very small curve area, uh, which indicates high strength but also low toughness, or so-called brittle. And then metals, they have a large curve area, so it is high toughness. And for polymer, it is in the middle, moderate area, so it has good toughness or medium. For example, like ceramics used for cutting tools or engine parts need hardness, and for steel, for something that need toughness like bridges or buildings, and polymer is how they can absorb energy. So the conclusion, the tensile test show that steel have the highest strength for 419 megapascal and the ductility 29% elongations, while the aluminum moderate strength 212 megapascal with lower elongation. And then we can rank all of this from the strength and stiffness. The first one is steel, second one is aluminum, the third one is PLA, and the fourth one is HDPE. While ductility followed the opposite trend and the experimental values were consistent with literature despite minor deviations due to specimen preparation, grip slip, and measurement limitation. Thank you.